Today we will learn about the levels of control or degree of control that you can have in a system. We will learn the difference between centralized and decentralized, and then we will understand the peer-to-peer architecture and its flavors, and then we will learn about system design, where we will discuss synchronous versus asynchronous networks and the type of failures that can happen in your system, and how to properly reason about designing your distributed system. There are two levels of control in distributed systems: centralized, which are systems that are owned by one single entity, a person or an enterprise or a company, for example, or decentralized systems. Decentralized systems are systems that are not owned by any individual, for example, Torrent or the Tor network or Bitcoin. In order to create such systems, whether centralized or decentralized, we need to first understand the possible ways we can architect our system. In the following diagrams, we won't be representing switches or routers because that information would not affect how our distributed application or system should work. You should always keep in mind that a distributed system is not the same as a network. A network could be running multiple distributed applications or systems at the same time. It's the same difference between apps and a physical computer. The traditional and the simplest architecture is the client-server architecture, where you have multiple clients all connected to one server. This architecture is very simple and it's easier to maintain and physically secure the server. But it has some drawbacks. For example, when a huge number of clients start making requests for this server, the server will become a bottleneck. Generally, the server is owned by some entity, and therefore it is a centralized system. And then we got the peer-to-peer architecture. In the peer-to-peer architecture, the difference is that each node or computer could be both a client and a server at the same time. So each node could ask for something, he could make requests to the whole network, or he could also play the role as a server and reply to other requests. And as we can see, each node has a specific number of other nodes connecting to it. So uh, these are called neighbors. For example, this node has 1, 2, 3, 4, 5 neighbors, but this one has only one neighbor, which is this one. And you can, the cool thing about peer-to-peer networks is the ability to architect your network pretty much however you want. You can uh, make this node connect to this one, or you can restrict the number of connections. For example, when this one tries to connect to this node, that would fail, would be impossible. And they are very flexible. So that's the cool thing about peer-to-peer networks. And it also depends on the algorithm you are using. So an efficient algorithm could actually beat the client-server architecture in terms of efficiency of retrieving data, but sometimes it would be worse. So it depends on your algorithm. And there are actually two types of peer-to-peer networks. There are unstructured overlays, and by overlay, I just mean the logical network, not the physical network. So how they are connected to each other. And in unstructured overlays, the network graph is pretty much random. So generally, they don't have a restriction on how nodes should connect to each other, but you would obviously have a certain degree of maximum neighbors, as we said previously. And also the data doesn't have to live in a one specific place. So if this node is looking for some specific data, let's say that he is looking for an image, and the best way of looking for that image is just by requesting its neighbors. So he would ask whether their neighbors, his neighbors, have that image. And if those neighbors don't have that image, they would forward that request to their neighbors, and so on and so forth until he reaches the data. So let's say that image exists in this node. So this one would send a request to all these 5 peers, and this one and this one, they would forward their request because all of these don't have the image. And then this one would forward that request to this one, and from this one to this one, until finally we reach the image, and then reply would go back. But this node could delete that image, for example. The image could be in another place, so it could be in here. So generally getting a reply is not always deterministic. So it is undeterministic. The only way you get data is by relying on your neighbors. And then we got the structured overlays. So in the structured overlay, the network graph has some form of a structure. For example, the ring network or the mesh network. In the ring network, each peer is connected with 2 neighbors at max. So it forms this cycle right here. And in the mesh network, each peer is connected literally with every other node. So they would form a mesh. And the difference between structured overlays and unstructured overlays is that data exists within a specific place. So you would have some form of a deterministic distribution of your data. So for example, I would say in my ring network here, I would say every image that starts with the letter H should always exist within the 4th node. So all the other nodes, when they start fetching for an image that starts with the letter H, they already know which node to ask, and they already know how much time it takes to get a reply. For example, this one right here, when he starts looking for an image that starts with the letter H, he wouldn't ask this one. He would already know that this node is responsible for that data, which means that getting information or routing information is deterministic. And that's the difference between structured and unstructured overlays. Knowing the network architecture does not mean that you know the level of control. For example, if one single entity owns all of these computers, it means it is a centralized system. In fact, big tech companies, they don't really use the client server architecture like this. So they would have a hybrid architecture where they mix the client server architecture with the peer-to-peer architecture like this one. So from the perspective of the client, he just thinks that he is connected to one single machine or one single server, but in reality, the company wants to make their servers or their application or system more scalable, and so that it could handle more requests. So what they do, they create a ring structure like this or a mesh structure to make their servers handle more requests. For example, I could say that this node right here or this computer would handle all the requests that come from 2 continents. For example, let's say that these are 2 continents or 2 countries. All of the requests would be routed to this node right here. Or I could say that this node would handle all the requests that come from Asia. So all requests that come from this continent would be handled by this one, and so on and so forth. So in this case, all of these machines or computers are owned by one single entity, which make it a centralized system. But that doesn't mean if you have a server, it means that your system is necessarily centralized. So it all depends who owns the system. For example, people could actually create their own servers like this. So I have this server which is owned by someone, and then this server right here which is owned by another person, and so on and so forth. So I changed the colors just to represent that there are different owners for these servers, and they could connect with each other to make a decentralized system. So I cannot point the finger and say this system is owned by one single entity. So, and you have this hybrid architecture. When someone gives you a problem, you should always know what the system model is under which you are trying to solve the problem. Modeling the system means to give a formal definition of the components of the system. Example, we have n processes denoted by pi. So P1, P2, P3, P4, and so on and so forth. And you can denote events by saying EI. So you can say event 1, event 2, E3, E4, E5, 6, 7, and so on and so forth. To just give a formal definition of the components. To understand the fundamental building block of a distributed system, it is necessary to consider the following questions. So whenever you try to model a distributed system, you should always try to answer the following question. The first thing that you should ask yourself is, what are the entities that are communicating in your distributed systems? Are these threads, processes, agents, nodes, so on and so forth? The second thing, how do they communicate? Via an API, RPC? What potentially changing roles and responsibilities do they have in the overall architecture? Is it client server? There are two distinct separate roles in client server, meaning a node can be either client or a server, but not both. Or is it peer-to-peer, where each node implements both the client and the server, which means equal responsibilities? How are they mapped onto the physical distributed infrastructure, which means what is their physical placement? To properly address the problem you are solving in any system, you should always ask yourself, what are the correctness properties of my system in terms of liveness and safety? Your solution is said to be correct only if it satisfies the liveness and safety properties of your system. So essentially, every distributed system or any system has some properties that represent the liveness of the system or the safety of the system. Okay, so let us try to understand what we meant by that. So in here, I just have a simple distributed system made up of 4 processes. Each process has a specific state, and these 4 processes, they form this ring structure. So it's kind of like this peer-to-peer network, and they are connected with these channels. So these channels will transmit messages, and the sole purpose of these messages is to increment this variable value right here. For now, it is super simple distributed system. So when P1 sends a message to P2, that process P2 will increment its value from 2 to 1. Super simple and super clear. The way we formally define our system is by saying the number of processes. So we have 4 processes. So this is the set of the available processes. We have P1, P2, P3, and P4. And how many channels? We have 4 channels. So this is the set of the available channels. We have C1, C2, and C3, and C4. Okay, so the state of my system, the state of all of this system, is equal to the state of each individual process plus the state of all the channels. So I can say that the state S of my system currently is equal to, and I can say P1 has the value of 5. So this is super simple. And here I just have one simple variable, should I say, and then I have P2, it has the value of 2, and then P3 has the value of 6, and P4 has the value of 8. And then, of course, I need to also describe the state of the channels. So I can say C1 has currently the value of M1. So it is in transit. It's still didn't reach P2. Okay, so it has something inside it, so it is currently transmitting M1. So the message has been sent from P1 to P2. So I say C, it has the value of M1, C1 actually, and then C2 has the value of M2, and then C3, it has the value of null, so it is currently not transmitting anything, and so does C4. C4 also has null. So this is currently the state of my system. So it is equal to the state of all the processes plus the state of all the channels. And your system will change its state, of course, by these messages. So in general, we call events. So it could be these messages, and or it could be something internal. So anything that changes the state of your system, let's just call it an event in general. So your state S0, let's say that all these processes are have the value of 0, and then when you trigger an event in your system, whether it is something internal or something external by another process, we call it an event. So events, they change the state of your system from a state to another. So it starts with S0 and then it goes to S1 and then another event 2. It changes to S2 and so on and so forth. And the thing that you need to understand is that there are some good states and there are some bad states. Good states or correct states are desired states. They are states that were intended by the application. So, for example, if I intend to increase the value of P2, I send a message from P1 to P2, this one, message M1. So when the message is reached, this value should be incremented from 2 to 3, okay? So it should be incremented, which means the state of my system changes from, let's say, S2. So this is, let's say that this is the third state of my system because we started from 0. And with this event, which is just sending the message M1, let's just call it E3, it changes to this new state, S3, where the value got incremented from 2 to 3. This is a good state. This was intended by the programmer, or this is a desired state. But let's say that something wrong happened. Let's say that a bug happened, and instead of incrementing, we decremented from 2 to 1. Now our new state contains a not desired state, a faulty state, a bad state. This is a state that we don't want. So essentially events, they change the system state from good states to bad states, or from good state to good state, or from bad state to good state, or they keep bad. So you have essentially either good states or bad states. And this applies for any system out there, not just distributed systems. So it applies for any system. Every distributed system could be defined also by the set of its properties. In this case, let's try to define a simple definition for our system. The first property that our system has is that no message is delivered unless it was sent, which means that all messages have to be sent by some process. So you cannot somehow pop up some message in the channel and send it in here. So you cannot tolerate messages being spawned in here in the channels and being sent out of nowhere. That will break your system. That is something that this is a property that if you break, it will take your system to a bad state, an undesired state. The second property that we want our system to have is that every message could be delivered or lost. So that's okay for us. Every message, it could be lost in here. So there could be a bug in the routers or switches in between, in this channel right here, and the message could be lost or it could be delivered. Now, every property could be categorized as a safety property or liveness or both. So let's try to categorize our properties. Safety properties means are properties that if you break, they will break the system. They will lead, if you violate those properties, they will take your system to a broken state, a bad state, undesired state. For example, if I get a message and let's say that some router got hacked and I have a message in here that is in transit in the third channel out of nowhere. So let's say that some hacker hacked the router and this message M1 has been sent to P3. This will break my system. This is an undesired event that changed my state from a good state to a bad state, and it broke my system. So which means that this is a safety property. Liveness properties means that something good will eventually happen. So let's see this one. So every message could be delivered or lost. There is actually no way of trying to break this. So messages could be lost. If you try to not deliver, it still satisfies the property. And if you deliver the message, it still satisfies the property, which means that this is a liveness property. If you take too long to deliver a message, it still satisfies the property because it says every message could be delivered or lost. It didn't specify the time it should take. So I can take hours to deliver a message and I could stall the system for hours. The state could not be changed for hours, but I always have the possibility of my state progressing towards something good. So which means that this is a liveness property. And this is just a simplistic definition for my system. And later on in blockchains or in distributed ledger technologies in general, you will have a more complex system with a lot of properties. And it will be great if you can categorize those properties to safety properties and liveness properties to have a more comprehensive view of your system. The next question that you should ask yourself is, what are the timing assumptions? So there are two types of networks. There are synchronous networks or asynchronous networks. Synchronous networks are networks where the following bounds are defined. You know exactly the time to execute each step of a process, and it has lower and upper bounds. Each message transmitted over a channel is received within a known bound. Each process has a local clock whose drift rate from real time has a known bound. So you know exactly how long it takes to execute something, or you know exactly how long it takes your system changes states. So everything is known when it comes to timing of processes and networks. So that's why we call it a synchronous network. And then we got partially synchronous networks where time and bounds are approximated. So you don't know in the beginning exactly how long it takes your request to be received by the others and to be processed, and then you get the reply. But eventually you will know that. So let's say that you send a request to a client. First, it took 5 milliseconds, and then it took 6 milliseconds. So you don't know exactly, but in time you can approximate it towards, for example, it takes at max 10 seconds. And then we have asynchronous networks where you have no idea about the upper and lower bounds. So nothing could be inferred, which means messages can take arbitrary amounts of time to be sent across a network. The internet is in this second category. It is a partially synchronous network because timing bounds are approximated, and we rarely have synchronous networks. After answering the timing assumptions, you should always ask yourself, what are the type of failures that you can tolerate in your system? or what type of failures that can happen in your system so that you can create an algorithm to tolerate them. Because processes may fail in four ways. The first way is called crash stop, and it just means that a process stops taking steps. It simply crashes. The second type of failure is called omission failure. Unlike crash stop, the process is functioning, so it is taking steps, but has inability to send or receive messages. So in omission failure, we have a communication problem. And then we got the crash recovery, which means that the process might recover after crashing. So it can have the crash stop failure or the omission failure, but in time it can recover and execute correctly, and then it can crash again and then recovers and so on. And then we got Byzantine or arbitrary faults. We have some processes that are deliberately causing malicious attacks on the system. Could be a hacker or a virus. So in general, someone is trying to break the system. So a node could be called Byzantine node if it is malicious. It is trying to work against the goals of your system. A process is said to be correct if it does not crash, or if it crashes and recovers. But if it just crashes, it is called a faulty node, not a correct node. And there is a hierarchy of process failures, which means if your algorithm works correctly under a general form of failure, it will necessarily work on these special forms underneath. Let me explain what I meant by a hierarchy of process failures. So if I create an algorithm that solves the omission failure, for example, which means I create an algorithm that can tolerate processes having the inability to send or receive messages with each other. So automatically, if I can solve this and they start communicating, by definition, they are taking steps, which means I already solved both of these. I solved crash stop and I solved omission failure. And then if I create an algorithm that solves crash recovery failures, or it can tolerate crash recovery, it automatically means that I solved both of these omission failure and crash stop failures, because in crash recovery, a process can execute and then crash and then execute and then crash again. Automatically, it is communicating, have the ability to communicate, and it is automatically taking steps. And then finally, if I solve Byzantine faults, it means that I solved all of these plus more. So if I create a distributed system that tolerates malicious nodes or Byzantine nodes or Byzantine faults, it means that I solved crash recovery and omission failure and crash stop. And distributed ledger technologies, they create algorithms are called BFT or Byzantine fault tolerant. So those algorithms that you hear about in distributed ledger technologies, even if you have in your system malicious nodes or hackers trying to break the system, they can't, because your algorithm can tolerate that type of faults. So a malicious node could actually make all of these type of failures and even more. So he can make some nodes simply crash, or he can make nodes have the inability to send or receive messages, or he could also make nodes work and then recover, crash and recover, crash and recover again. And he can do more. He can create viruses, he can do more damages. So all of these are special types of Byzantine faults. So again, crash stop is a special type of omission failure, and omission failure is a special type of crash recovery, and crash recovery is just a special type of Byzantine faults.